My name's Colin Chapman and I'm a master teacher for the Victorian Academy of Teaching and Leadership, which is a new government initiative to work with highly accomplished teachers across the state back in Australia. And the idea is to push these highly accomplished teachers to think more broadly about taking more of a practitioner approach to their teaching, being active in their field, not simply just describing the field. And so some of the things that we've been doing to encourage this include using Wolfram System Modeler. So extreme citizen science is a posture that we've been encouraging. And this idea of extreme citizen science talks about the students just not simply replicating something they've seen or just copying a recipe book and doing some experiments from a textbook. The idea is that the student is engaged fundamentally in the deep questions about instrumentation, data collection, data analysis, how to form a good question. All these sorts of things are important to the idea of extreme citizen science. And it does build on some of the frameworks which were developed by Olaf Palmer and others in Europe with regard to common security and the idea that citizens themselves should be involved in collecting data about their environment in order to conduct actions in the world. And our posture in education in Victoria in particular is about students acting in the world, not being simply brains in vats on tables, but people who are engaged with communities, environments, and so on. So we find System Modeler very useful for students to be able to take this posture and be able to communicate ideas. So I'll talk about our study. So we have a systems engineering course, which I wrote 10 years ago, I suppose now. And system engineering is offered at year 11, 12, which is typically the age group is 16, 17, 18-year-old students. So this is pre-university. And the course is written to have students develop and model a plan. That's fundamental. We're not very interested in people or in students just simply describing a system or listing features of a system. We want them to model a system and take that risk. And this is a very risk-rich study, which encourages students to think about modeling in a very deep way. The expectation is that the models will not work out terribly well. So as we know, typically our models end up being, start off very idealistic. The classic physics model, which is you model each cow that you see as a sphere, very idealistic model, but not realistic. Right? So we want students to make their way through these idealistic models to models that are less perfect in order to be more realistic. They're expected to develop a controlled electromechanical response to a problem, situation, opportunity, or need. And this electromechanical response has to have the electrical and mechanical aspects of their design response work together using feedback of some sort. And we also use a narrative mechanism, which is why we're really keen on notebooks, because notebooks allow the students to not simply describe what happened, but to give important vignettes as they're going along as to what happened during their particular project. So those vignettes can include things such as simulations, video, audio, all sorts of material in order to thicken a description as to what happened during their program. And we do reward risk. We move beyond rhetoric. And this is one of the interesting challenges that Conrad Wolfram throws up to us all with regard to the what he calls the maths fix. We struggle against an assessment program which is rewarding recall and not much imagination and not much risk taking. So in this study design, and I'll show you how we structure it, we try to reward risk in a real way. We expect people to develop an intention, and then we reward them when the plan doesn't go to plan. 25% of the marks for the project are for the thing becoming a train wreck and for the students getting out of the train wreck in some fashion. So we're expecting them to research, model, simulate, experiment, take risks, And this plan is really very broad. So it's not just, I'm going to build this. This is step 1, step 2, step 3, Gantt chart style. They need to actually plan how they're going to learn during the project, because these aren't set projects. These are things that come from the students themselves. So if a student is working in a rural area, they may decide they want to develop some sort of automated gate system for cattle on the property. It's not a project I tell them to do. It's a project they work out themselves from the beginning. Right? They think about the question that's important to them and appropriate solutions and so on. So they need to develop a plan for their learning, time, resources. They need to keep an agile idea in mind. So the idea that they're going to make something that works in some fashion, assess, evaluate, go back, redesign, and keep going and keep iterating their designs. So the idea is that the students aren't doing a one-shot project. It's a project that has many points where there's some sense of completion of some aspect of the project itself. And of course, there should be testing and there should be evaluations. So you'll get these slides. The words are small. I couldn't fit them otherwise. So, but you'll get them and you can have a read for them. But you can see this first one is simply an investigation. So over there at the far end, generally students are aiming to get that higher mark. So that's where they're going to put themselves. You'll see that the verbs as we go across start to talk about things such as justify and so on, explain. And at the bottom end, it's really just like a listing activity. So these verbs encourage the students to not just say, I'm going to do this, but also give an argument as to why it might be a reasonable thing to think or to do when they're going through. So they develop a design brief, which is a response to a problem. And as I've said, it's a unique problem that they work on. It's something that comes from them. So we've had students who have done such things as build drones that will go above roadways and collect pollution information and give some sort of map on a GIS type system as to what the pollution plume looks like. We've had students who have made autonomous aquatic rovers that go out into bodies of water and make water samples and then report back as to things such as turbidity and other measures of water quality and so on. So a broad range of projects are suitable for these students. And again, it's from them, it's not from me to them. My job is to be the character on the side who provokes them to keep thinking differently and to encourage them when they're having their successes and to have them think about when things aren't going to plan, their job is to go back and think about what's happened. And sometimes that think about extends right up to the question in itself, right at the very beginning. So you can see that they also expect at the very beginning in this section here to develop some way to evaluate success. And we want them to do that because we want them to, at the end, think, there are a whole lot of things I could have evaluated that I hadn't thought about before. So that's part of the learning process. The way I thought I might evaluate some of these qualities, I've now changed my views over the extent of the project. And when they change their views, when they make a different decision, they're rewarded for that in the end of this program. Right? We don't just simply say, take a risk and then bye-bye. We say, take a risk, offer to us what happened during that risk taking, and we'll reward you for it. So here we've got some work on research and modelling, and this is where Systems Modeler works for us as well as Mathematica. And we're expecting the students to model their system in some fashion. And they will be modelling subsystems as well as the complete system. They can use Systems Modeler for that, but also they augment it with scale models and also models of subsystems themselves. We want them to be modelling in many different ways because we want them to think about the differences in the models and the sorts of information they can gain from those different models and what the advantages and disadvantages of models were. So to give an example, there was a student who wanted to make a wheelchair lift with a very short throw for a neighbour. And so they did all this wonderful modelling And part of the modeling was calculations. So they did all these vector calculations, beautiful piece of work, and did a scale model. The scale model worked very nicely with small linear actuators, and it did exactly what it was expected to do. And then they built it, and the whole thing was a flop because the scale model didn't model the properties of the materials that they were going to use in the end. So a lot of warping and all sorts of other issues. And so the device worked once and was not in a state to work again. So the student comes away from that experience understanding there's more to modeling than just scaling dimensions. There are all sorts of issues with regard to properties of materials and so on. So modeling is really central to the plan, and it's part of the plan that will not go to plan, and we expect that to happen, and we reward it. Right? This is part of the risk-taking posture that we're very keen on. And now this is the planning of the creation of the system, and this is something that we lock in. So this planning aspect will go on for typically 2 months or so. And once they've done all this, those documents are submitted and they're kept with the teacher, locked away. So the student can't modify the original plan and the intent, right? So this is the warts and all plan. It's to allow the student to be able to say, I did fail at the end. Here's what happened compared to what I intended. And they can make maps, right, connections between those two things, and give us a narrative as to the decisions they made. How did they notice the plan wasn't going to plan? What did they do as a result? Did they go and try to buckle down and make the plan work no matter what? Did they replan? Did they replan processes, or did they go back and actually replan the response to the stimulus? Right? Did they think that perhaps they thought, I'm going to develop a response just by myself to this difficulty. So, but as they've worked with the users, they've realized, oh, I need to work with the user themselves. Right? So to incorporate them into the planning. So an example of that would be, there was a project recently for a person who was using a wheelchair, and they kept backing into their dog at home. And so they wanted some sort of system to be able to warn them that the dog was present and that they wouldn't bump into the dog and so on. And the student originally just started planning the response and didn't talk to the person who had the need. And so an important part of the change of their plan was going back to the user themselves and getting a deeper understanding of what their requirements were and so on. So these are important sensibilities that we reward through the fact that they can fail, and we make sure that planning is locked in at the very beginning. So once this plan is locked in, the teacher takes that and places it on the rubric and so on. The student goes ahead and gets into the build. So I've talked about this. We call it an e-record of evidence. When I came into the study, everything was in a paper portfolio and submitted, and it was a dead document. It didn't really say anything. Right? You couldn't experience what the student had experienced throughout this process. So we have an e-record of evidence, and that contains text, audio, images, video, and it's really nice now with the video tools on Mathematica that we can now incorporate that more strongly into the e-records. Models and simulations, all sorts of things. Anything there that gives us a thick description of the experience of the student as they progressed through their journey in systems engineering. We expect them to recognise what's going on with regard to the implementation of their plan. It's either going to plan, not going to plan, more likely not going to plan. We expect them to document, we expect them to replan, remake, re-recognise. Right? Keep going through that process, and to be aware that there's more to the project than the nuts and bolts of the project. It's situated in an environment which has users, which has laws and regulations. So students are expected to go and make sure that whatever they build is congruent with the laws of the land and the regulations and so on. These are all parts of the ecosystem that they need to be working in. And so we can see here we've got use of tools and so on. And this is the making aspect. And we know that sometimes the students will build their own tools. And so one of the examples I'll show at the end is a polarimeter. So the students build their own instrumentation and implement it and so on. And we reward that as a narrative process full of images, because nothing talks about how somebody has used tools safely and reasonably than a video of them actually doing it. Right? So we've gone away from students describing how to do things safely to a student actually having to physically do something safely, and you see it in video. Right? It's very compelling evidence. It also relieves them of a burden of having to write prose. And so here we've got, you can see the progression goes from with support at the low end to independently, produces an operational integrated control system that addresses the context, considerations, and constraints of the design brief. So this is the response to the problem that the student is interested in. Described in a work plan with documented modifications. Now, you can see that as we move along to the high end, this idea of context comes in, right? Technological solutions are not context-free. And so we expect that as the student's moving along, that they show a stronger understanding of the context in which their solution is being developed. And that context is very broad, of course, including environmental considerations. So this is a nice criteria. So there are 8 criteria altogether, 12.5% for each criteria for the project, and the project contributes 50% of the total mark for this matriculation subject. And here we've got diagnostic test procedures and interpreting test data. And it's nice to have this because, of course, Systems Modeler and Mathematica support this very, very well. It allows them to display and interpret data in a variety of rich ways. The interesting thing here is you look at the indicators over there. They need to give a reason for the diagnostic test. They need to explain how it's set up. They have to conduct tests and they have to generate and then use the test data. This isn't a one-off test either. So this criteria is interesting because it's almost the whole process, the system engineering process in one criteria. So if the test is not satisfactory with regard to the quality of the data, precision, accuracy, whatever it might be, they can iterate the test and keep improving the test, and we reward them for going through that process. So the next 2 sections, which are worth 12.5% each, so 25% of the full mark, is for all of this, discussing how the plan did not go to plan, reflecting towards planning differently, thinking about agility as a process for intimate response, and most importantly, to critique modelling itself. Right? What are the things that they've done in the modelling experience that's important to engage with critically so that we can have a more mature approach to modelling. And this, in Victoria, my state where I came from, where we had about 2 years of shutdowns during the pandemic, there was a lot of questioning of modelling with regards to virus spread and so on. And the community wasn't ready to critique modelling. So this process here in our study is an attempt to have students develop those sensibilities to understand that modelling is fundamentally a flawed process, and that's part of its strength. So we know that weather forecasts became more and more accurate when supercomputers came along, because you can model a weather, spit out a result before the weather came, make a comparison and adjust the model. We expect students to develop that sort of sensibility with regards to modelling. It's to say that a model's failures are an important way that the model can be improved. Similar to what I said at the very beginning, which is we make the model less perfect in order to make it more realistic. So here's the reward here. So we reward them for time management, We reward them for evidence of progress, risk assessments, diagnostic testing, and that last bit there at the very end there, and you can see that important verb, justifies. Before then it was explain. Before then it's describe, identifies. So we've got a whole Bloom's taxonomy of engagement with this process, from just listing activities right through to justifying. Justify your decision making. So what's central to our study is that students have to have an opportunity to make decisions, right? So that they can then justify what those decisions were. And those decisions, of course, are up for debate. Yeah. And there's the last section is about the system engineering process in general. I'm going to just skip ahead. So one aspect of the study that we're interested in having the students do is to explain and talk about how various subsystems are working. And the voltage divider network for us is a bread and butter circuit, because it means that our students from low socioeconomic backgrounds, all of them can access a $1.50 light dependent resistor, or a photoresistor, or a thermistor, or whatever that might be. So it's a simple circuit. It can be implemented on an Arduino, but here we've modeled it in Systems Modeler. And it's a 5-second process, and the circuit is very simple. That's it, the test piece, so they can build their little voltage divider network. I've got a photoresistor here, but I've also got flex sensors and thermistors and all sorts of resistive elements that can just replace the LDR. So we can build this. I've put a ramp voltage in the model and then pulled it into Mathematica. And one of the advantages of pulling the model into Mathematica is they can use Mathematica as their e-record of evidence. And it means the person who is looking at their work can actually run the simulation. Right? It's not just a dead document that describes their simulation. It actually runs it itself. And I won't bore you with that, because all of you will know how to do this, of course. But there's a beautiful photo of me. We produced a whole lot of videos for our state education department for teachers to be able to build these systems. But this is the simulation for that voltage divider network pulled into Mathematica with manipulates. It's just a beautiful piece of work that students can incorporate into their e-records of evidence, which shows the experiment. Right? It's a living experiment. It's not something they're just describing as dead. And it's a nice illustration too, because when we use a ramp voltage, we can see the proportion of the voltage is always the same throughout the whole simulation. And they can change the resistor values for the different proportions and so on. So not only are they saying, I'm using a voltage divider network, but here it is, this is how it works, and so on. Right? That's part of their record of evidence, is this theoretical exposition as well. Right, so this next model is through ModelPlug in Systems Modeler, which I really enjoy using. And this one here is a system that detects whether a light level in the room falls between two values. Now, it uses a voltage divider network to determine light level, but of course we can replace the LDR with a thermistor, and we can do it for temperature. We can put a flex sensor in there, and we can measure wind speed in some fashion, right? So there are all sorts of things that we can plug in. So it's a general purpose model. The model is worth exploring and playing with. There's an example model with just a above or below measure. This one's got a 2 measures, so it's looking whether the light level is between 2 values. And if we, so here's a simulation, and why this simulation for, no, this is not the simulation, this is the actual working trace. And why this is really cool is we've got the light level up here, squiggling all over the place because I'm waving my hand frantically above the LDR, but they can see the response of the system, right? So this is the digital output. So it's a nice demonstration that their system is working, but also how it's working. You can see I'll put the two bounds as well to show that when the signals between those two bounds, we expect to get a digital high and so on because of the logic we set up. It's a really nice demonstration. It's something that can be included in their e-record of evidence. And it shows a good understanding of what's happening in the system, not just a follow a recipe type approach. I think I'm doing all right for time. It's not bad. So polarimeters are cool. Thank you. So there are some substances, fluids that exhibit chirality. So sugars, for example. So you can set up a system with two polarizing films, and you can put the chiral solution, sugar solution in between there, and you can determine transmission of light through it. And it gives you a measure of concentration. And what's really nice about it is this has to be calibrated, right, as all these systems do, including the LDR system and so on. So this calibration piece is really nice because it's not a very precise experiment to be able to do. A lot of error involved, and the students have to be able to deal with all that error and all that noise. So the Polaroids are also very cheap. You can get them online for next to nothing. You can also hook up the Polaroids to a little servo motor, such as this. It's also cheap. And the students can automate an experiment where they're measuring light transmission as the Polaroids rotate and get an idea of the chirality of the solution, and then calibrate it for a 10% solution, 20% solution, and so on. So it's neat because we can use, of course, the students can record the whole process, including all the things that went wrong in the notebook. So the notebook is not proud about being perfect, right? And that's its strength. It records everything that happens, right? And people are encouraged to keep it. So again, these are things that all of you will be able to do quite happily, but we've just taken the data together and we've taken some averages and made a little plot there. And we can see that there's a peak at a particular angle that we've associated with the rotation of the servo and so on. So the student has got a measure for 10% sugar solution. This is what the peak is. So if they see that peak, the unknown must be that concentration and so on. So I think that's it. So that was very rushed. As I say, ordinarily we would actually go and build these things as we're talking about them. So it's a bit more interesting, but short time, so more descriptive. I hope that was useful. I'm happy to talk with people if they wish. It's a small microcontroller. It can be tethered or untethered. I don't think we can quantify risk. I'm trying to think of the SI unit for that. It's not clear to me, but the response to risk is what's important to us. And you can see that the rubric has got a range of responses, so they can explain what they did or describe what they did, and that's sort of middle order. They can justify decisions they've made, and those decisions could go right back to the original question as well as to other aspects, but that's how we reward it. Yes, so the pandemic was a good example of that. So we had 2 years where students barely were in the workshop, and the projects were problematic, but we were able to use their prototyping activities, the calibration activities as a way to reward risk-taking. So we were able to there's breadth in our study to be able to take aspects of what they've done and to get measures of, to satisfy some of those criteria. But we've also had students here where it has completely failed. That wheelchair example, that student went on to get a very high mark and to get a good place at a university. And it's because of that reflection upon the modelling process. And subsequent to that experience, that students come back and been very thankful for that failure. It's been important for their success as they've moved on. I think that's me now. Thank you very much.